Hello, welcome back. We are discussing section 1.6, one-sided limits and continuity. In particular, we're going to tackle this second learning objective, explore the concept of continuity and examine continuity for functions. So let me get to slide of interest. So our initial approach to continuity is just going to be from an intuitive kind of perspective. I know I use the word intuitive, but and that certainly doesn't seem to apply to math in many instances, but I think even this definition could probably appeal to some people. So we'll just say initially that a function is continuous if you can draw its graph without having to pick up your pencil. So you can imagine all these kind of interesting waves and curves that you could make for some function that doesn't involve having to pick up your pencil and start somewhere else. Any one of those functions that you're drawing that doesn't involve you picking it up is continuous. So of course, there's some issues with this from a mathematical standpoint, but that gives us at least a little perspective. So one function we could imagine in nature, perhaps, if we pretend that this is, well, we don't have to pretend if it's a regression function. So if we pretend we've taken some stock values over time and drawn a smooth curve to try to connect them as a curve of best fit, then this function is continuous because we could follow this graph along, and at any given moment, there is some stock value. Now, if you're thinking perfectly accurately, these values might flatten out when the stock market's not in session, but we'll just remember that this is a regression curve over time. And the main thing to think about is that at any given point, there is a stock value. So there's no gaps horizontally between these things. And then maybe from a pharmacophysiology perspective, we could look at drug concentration. And this also being over time implies that at any given point, there is a concentration of drug in the bloodstream. So these would be continuous functions by that intuitive notion because we could draw them without picking up our pen or pencil. So a little bit more formally, this is in a section about limits, so it may come as no surprise that this would involve a limit, but we say a function is continuous at some value. So notice we're only talking about a particular point on this function. If we can say, look at this two-sided limit of the function, and what you get is f of a. That is, one way to think about this is that the limit gives you what you expect from the graph. So, in other words, if the limit as we approach a, this value a, agrees with the actual output, then the function's continuous. And just to revisit the graph for just a moment, if we pick one of these pictures to work with, if we imagine that what we're really interested in is continuity at the point 2, for instance, what this definition is supposed to suggest for us is that if we come in from the left side and we come in from the right side, we follow this graph in, the graph is pointing toward this output. So the way we could break this and create I mean, it feels artificial, especially in this scenario, but if we had a little open circle somewhere, and then the actual function definition was somewhere else, then as we're creeping along the graph toward this particular input, the limit would be pointing toward that open circle. What the limit would expect is basically whatever this value in the open circle would be. But if you actually ask this function, hey, what is your output at this particular input here? It would tell you this height up there. It would not tell you what the open circle is. So if we poke a little point out of this graph, suddenly this is no longer continuous because what the limit expects is not the same as what the function output actually is. And if you notice, if we tried to draw that particular thing with the green situation, then we'd have to pick up our pencil, draw a little circle up here, and then keep drawing. So our intuitive notion of continuity would break in that case. So that's our formal definition for continuity right there. And exploring it with a piecewise defined function that we had from the last video, we've got a definition for x values that are at most 1, and then a separate function definition for x values that are greater than 1. And the claim is that it's not continuous at x equals 1, and that's because if you recall from our last video, we were responsible for computing the limit as x goes to 1. And we did that by computing x goes to 1 from the negative side, which involved this expression, and x going to 1 from the positive side, which involved this part of the definition. and we got two different numbers. We got 4 and 0 for those respective halves. And that implies that this two-sided limit doesn't exist. Moreover, what that implies is that if this thing doesn't exist, then it can't be equal to something else. So the output of this function at 1, so if you notice, just going back to our piecewise defined skills spelled with a Z clearly, piecewise defined skills means we plug in x equals 1. This must be the half that's in charge when x is equal to 1, since it's defined if x is less than or equal to 1. So this is the expression where we dump in 1. If we go to put in a 1, we get 1 minus 1 squared. That really is 0. So because the two halves didn't agree with one another, though, we never even got to see if it equals 0. And maybe an additional helpful demonstration would be to look at the actual graph of this function. So on the left side, here's that 1 minus x squared portion of the graph for x values that are less than 1. And here's the portion of the function for x values greater than 1, just this linear component, 3x plus 1. And if we use our intuitive notion of continuity, if I'm trying to draw this right there, I would have to pick up my pencil and keep drawing. So by any of these explanations, this is a way to see that this function is discontinuous at 1. Okay, so we've got an application to look at, although weak as it may be. So we've got a bag of rice that's going on a conveyor belt, so it's headed up at an angle, we could imagine. And then after 6 seconds, it falls off of it. And so what we can picture is that there's one portion of this that's going to model the height of this bag of rice for up to some point. It looks like 6 seconds. And then a different formula that's going to model its height after those 6 seconds are up. So it's our job to find the value of a. If you notice that there's this kind of unknown constant snuck in here, we need to find the value of a such that this overall function, the height giving the height h of t, which gives the height of the bag, we want it to be continuous no matter what positive value of t we put in. I guess positive because we imagine the conveyor belt doesn't start until t equals 0 or something like that. So before we can create a continuous function, we probably need a function. So we can construct a formula for this height, and this is one of those sort of magic appears moment, but remember that before it falls off the edge of the conveyor belt, 5 plus t it's a description of its height. So the only thing that needs to get attached to this is that it's only true when t is between 0 and 6. At the 6-second mark, something else takes over. So it's no longer going up at an angle, now it's probably falling downward, like getting pulled by gravity. So we've got this unknown constant a minus 16, quantity t minus 6 all squared. And that piece is in charge if we're 6 seconds or later after this conveyor belt started. And then here's the consideration. We're in charge of making h continuous. So the linear component, the piece on top, and the quadratic piece on bottom, if they were just listed completely on their own, if our entire function was h of t equals 5 plus t, you'd have no problem having that be continuous. There's nothing discontinuous about a line. And then maybe it's a little bit harder to ascertain the shape of this, but maybe you'll believe me that this is going to have t squareds and t's and then constants in it. So it's going to be a quadratic. And a parabola, if you can picture its graph, could easily be drawn without lifting up your pencil. So we have good reason to believe that that piece by itself would be continuous as well. So really, the only thing that could go wrong is where they meet up. And this is, you don't have to worry about definition this way, but the point of articulation, the point where these two things change definition, this one hands off to the other, that's where things could go wrong, because there's no guarantee that they hand off perfectly. So we're going to focus on making that handoff happen smoothly. And the way we can do that is that we don't know, we have this constant that's unknown in the equation. We can figure out what value of the constant would make both of these one-sided limits that are approaching 6 agree with one another. So if we take the limit as we approach 6 from the left side, doesn't matter which we start with, but if we approach 6 from the left side, we definitely have values of x, or t in this case, which are smaller than 6. And when you have values of t that are smaller than 6, this is the piece of the function that's in charge. That's just going back to our piecewise defined function definition. 5 plus t gets to call the shots as long as the t values are less than 6. Okay, well then we've got our great rational function theorem from the previous section that says if you've got something that's a polynomial, then all you'd have to do is take 6 and plug it in. And there we are. So the limit operator goes away, and now we've got 5 plus 6, we've got 11. Okay, so we actually got a concrete number from the left side. From the right side, now again, we're approaching 6, but from the positive direction. H of t now looks like this other half of the definition. So instead of being the linear component, if we pick values of t that are greater than 6, this quadratic piece is who's in charge. And again, making use of our nice theorem that says if you want to know the limit of some polynomial, or even could even be more complicated than this, a rational function. If you want to know the limit of somebody like this, and it's not undefined at 6, you might as well just dump in 6. So if we plug in 6, all of this becomes 0. So in fact, all of this is out of the mix except for a. And that's all we're left with. That by itself wouldn't be super useful, but given what we're trying to accomplish, we want the left side and the right side to have equal limits. So that's how we're going to finish this out. We take those two expressions. We got 11 from the left side, we got a from the right side, and we want them to be equal. So this actually does it for us. We found the value of the constant right there. So if we choose a to be the value 11, then this height function is continuous on its entire domain. That's it for section 1.6. We'll be back with chapter 2.